Okay. Good afternoon, everyone. This is a joint M-Cube Cosmic seminar, and I'm pleased to present Shu-Ya Chen. She's an Associate Research Fellow at the GPS Science and Application Research Center, National Central University, Taiwan. Her research focuses on GNSS radio occultation, that she'll call RO, I guess, for short. And its assimilation into numerical weather prediction models for severe weather events, such as typhoons and Mayu fronts. She has participated in numerous GNSS RO-related research projects. Her recent work emphasizes the impact of RO data assimilation on tropical cyclogenesis simulations and the evaluation of cloud microphysics parameters with polarimetric RO data. Welcome.
Thank you. It's very honored to be invited to give the talk. So actually, I'm very familiar in NCA, UCA, because I used to visit several times in MQ and also in Cosmic. So today, I will show the evaluation, my research work about evaluating the cloud microphysics parameterization in tropical cyclone with parametric radio occultation. So I'm from the National Central University. So our my affiliation was the GPS Science and Application Research Center. But from this August, our center have been upgraded and renamed to the Global Atmospheric Observation and Data Application Research Center. So we were including multiple observations for the research. And this work today I will present is collaborate with Bill Gore and also my colleague Shu-Ya Chen and some scientists from Spain and JPL. So first, I will give some introduction about the motivation for this study, and I will just give a brief introduction about what is GNSS RO and what is the PRO. PRO means the polarimetric radio occultation. Then the next and then following will show about the model configurations, and we're using the Wolf model, and then also to compare with the PRO data, we need a forward operator to calculate and transform the model variable into the same variable compared to the PRO data. Then I will show some comparison and verification about the simulations result. Then also we also do some sensitivity analysis by using the ensemble runs, and also there's some sensitivity tests to using different PBL scheme. Then finally is the conclusion. So we know that with the climate change, there's the extreme precipitation associated with the severe weather events such as typhoon has increased. So we can see from this, this is an IPCC report. It also shows that the typhoon events just increase over this region. And we know that many cloud microphysics parameterization schemes in numerical model are bulk parameterizations without a lot of details. So we want to, so this one, the evaluation of this parameterization has been a challenge. We know that recent year there's GNSS parametric radio occultation, we call it PRO. It's a novel technique that can sense the vertical atmospheric hydrometeors by acquiring the GNSS signal in both horizontal and the vertical polarizations. So in case some people not familiar with the GNSS, the GNSS indicates that the global navigation satellite system. Okay, so the motivation of this study is to assess whether the PRO observation can be used to evaluate the performance of the model called microphysical parameterization on typhoon cases. So we will just focus on for typhoon cases. Then here shows the just a cartoon to explain what is the radio occultation technique. So for example, here is the Johnson satellite, something, for example, just GPS satellite. And this is the low Earth orbit satellite like Cosmic or Cosmic 2. So we can see that when the signal passing through the atmosphere, because the air density different, then the ray path will have some bending. Then after it received from the low Earth orbit satellite, we can get in the bending angle and further retrieve the refractivity. And with some other information, we can retrieve the profiling temperature, pressure, and the moisture. Then the polarimetric radio occultation is very similar with the traditional radio occultation, but it just receives the signal by using a two linear polarized antenna. So this concept is introduced in 2009, and also the PAZ satellite is launched in Spain. They have successful launch in 2018, and this one, the PAZ satellite can just receive the signal by using the horizontal and the vertical antenna, so we can separate that signals. Then we, for example, when the ray passing through the precipitation system, then, for example, it's passing through a raindrop. If the raindrop is large, so we can see that the ray passing through this horizontal and vertically, the phase will be different. So according to the different phase shift, we can get in the vertical profile for the delta phi. Then, according to this, we can detect the hydrometeors when it's passing through the ray, when it's passing through the ray path along the ray path. Okay, so besides the delta phi from the PRO measurement, it can also get in the standard RO product like temperature, pressure, and the moisture, and also the refractivity and bending angle. So it means it can get extra information compared to the standard RO data. So here just show a example that in previous study, many study already compare the PRO data with other observation to show the characteristic of the PRO data. So here just shows that the PRO versus satellite image. Then we can see that with the warm color, that indicates that it's a high rain rate from that observed from the image, and with the high rain rate, then the delta phi from the PRO observation, it also shows a larger delta phi value. And for small rain rate, like the cold color, then it will show a smaller delta phi. So it indicates that the delta phi is very sensitive to the precipitation intensity. Then the other study also compare that PRO data with the radar data. So here just show the ray path from the PRO. Then this one shows a single profile that compare with the next ray from indicated by the red line, and the black line indicated from the path. So we can see that the pattern is very comparable. So now we want to focus on 3 typhoon cases. Here shows the typhoon cases we are using in this study. So they are Typhoon Broi and the Typhoon Metamo that occurred in 2019. And the third one is Typhoon Kampasu in 2021. And for Typhoon Broi, will be we want to focus more on this one because it's an intense typhoon and that just rapid develop, intensify to be a category 5 within 2 days. And the other two typhoon case will be more weak compared to the Broi. So here shows the model configuration. We using two domain using the WOOF model, and is the WOOF model version 4.2. For all the 3 cases, we just using the same domain 1 coverage, something like this. But for the individual typhoon cases, we will focus on the typhoon location, then to set a specific domain 2 for each typhoon case. So here shows the 3 boxes for the domain 2 for each typhoon. Then the horizontal resolution will be 15 kilometer and 3 kilometer for domain 1 and domain 2. Okay. Then for the model parameterization, they all the same for all the cases except the microphysics scheme. And there's no bogus vortex implementation in this study. So here shows that the setting for the experiment. So for each typhoon case, currently we have 3 typhoon cases, and for each typhoon case we have using two different initial conditions. One is from the Goddard FNL, and the other is from ERA5. And for each initial condition, we also conduct 5 microphysics schemes. They are Purdue Lin, WSM6, Goddard, and new Thompson and Morrison 2-moment scheme. So total, there will be 30 WOOF simulations in this study. Then here just show the initial time, and for each typhoon cases, we just focus for 18 hours. So this indicates the PRO data time, the time for PRO data compared to the forecast. So for each typhoon cases, there will be accurate for the more than 12 hours to accumulate the microphysics, and then we compare with the PRO data. Then here just a brief introduction about these 5 microphysics schemes. So for the first 3 cases, it all will be the single moment scheme, and actually we pick up these 2, the Purdue Lin and the WSM6, is because that is the suitable for the real data and high resolution simulations. And the 7, the third scheme is the Goddard scheme. We pick this one is because it separates the hail and the grapple separately to deal with that. And the other 2 is a double moment scheme. So to compare with the PRO, we need to convert the model variable into the delta phi. So here just show a simplified function, what we use. So this one, for example, the delta phi is the differences between the phase from the horizontal and vertical direction. And then actually that is contributed from the KDP. KDP is the specific parametric shift. And this one, the total delta phi actually is counted along the path, the whole red path. So we need to give an integral from the KDP along the path. Then how about to calculate the KDP? So it is also associated with the water content. So we just getting the simplified function as that introduced in these papers. and using this function to calculate the KDP. And actually, this coefficient, for example, the C is the Rayleigh coefficient at the L band. It's a constant value, but for the density and L ratio of the hydrometeors will be varied for each hydrometeors. So how do we decide which rho and AR to use? So we just refer the value that SS from the Purdue Lin et al. In 2022. They just consider the SS ratio that change with temperature, and the temperature that actually that is depending that the temperature dependence is supported by the theta observations on frozen hydrometeors. So it only provide the function that above the frozen layer and also below the cloud top. But we want to using more layers for the calculation, so we just getting the constant value when that value the height above the cloud top and also below the freezing layer. So this function is using for the frozen hydrometeors. About the liquid phase, something like rain, we're using a different function. So we refer to the Zhang et al. They calculate, they estimated the drop shape relationship about for the typhoon case, and they show this like the coefficient is the SS ratio is close to the 0.95 for the typhoon case. So we using this value and take the density for the equal to 1 for rain. So we can see that in this study, we using the function for liquid phase, something that just like the blue line is a constant. And for the solid phase hydrometeors, we just using something like the red line. Okay, so we can get all that information. So here I will show, as I mentioned, that we have two different initial conditions. So in the beginning, before the model simulation, we can compare the differences between these two initial conditions. So first one is, this one is for typhoon Boris, for example. Then this color shows the total precipitated water, and this is from the initial condition from the ERA5, and this from the Goddard scheme, Goddard initial condition. So we can see in the beginning, it already shows significant differences for the typhoon Boris circulation, and also Goddard initial condition shows a much intense typhoon compared to the ERA5. Then after 18-hour forecast, we can see that with different microphysics scheme, it also shows some deviation and differences between all these experiments. We can see, again, this also for the typhoon Boris. And the upper panel shows the initial condition from ERA5, and bottom from the GDS. And different, this shows different microphysics scheme. We can see that even in the beginning, ERA5 provide a weak typhoon intensity, but after 18-hour forecast, the typhoon intensity is still weaker than the GDS initial condition, but for the total precipitated water about the rainband, is for some microphysics scheme, it shows a larger and more intense compared to the GDS initial condition. For example, for the Goddard scheme, is something like slightly intense. I'm not sure is this clear or not. Or for the Morrison scheme, it shows intense compared to this one. Okay, so next I will show some general verification about the simulation result. Then this one just show the simulated typhoon check and we compare with the best check. So the best check is adapted from the JTWC. So we can see this shows the 18-hour forecast for the typhoon check. And for each typhoon case, we can see that the black line is the best check and the solid line indicate using the initial condition from ERA5, and the dashed line is from the GDAS. And we can see from the for the Boy typhoon, all of the simulated check are very similar, very comparable. And oh, I forgot something. For this one, because I will mention later about this one. Actually, the cross sign indicates the best check from the JTWC. So it's indicate that for each typhoon each simulation is always show a westward diffraction for the typhoon center compared to the best check. So we can see from this way, the best check is over here is also always show a westward diffraction. Then, and this one's for typhoon Metmore and the typhoon Kampasu. We can see that all of the case just show a very comparable simulated check for using the same initial condition. So for example, this one is from the GDAS initial condition. It all shows very comparable simulated check, and this one is from the ERA5 initial condition. And no matter which microphysics scheme used, it also show very similar patterns. So we don't know which one is better. So here just getting some sense about which ones perform better. So here we getting the average error for the typhoon check for all the 3 typhoon cases. So we can see the yellow line indicated the using the Goddard scheme and shows a smaller check error when using the ERA5 initial condition, and also it also gives the similar conclusion when we using the GDAS initial condition. It also shows a smaller check error. However, for the typhoon intensity, it doesn't show a consistent conclusion which one is better. Okay, so that just indicate like a synoptic scale or the environment around the typhoon check. Then here we also compare with the simulated result with the traditional GNSSR data. So here just show that there are few R data, and also there are 14 GNSSR data and 1 radio sound that close to the for each typhoons, and we just getting all that data and do the verification. So we can see that this one is verified in temperature, the room square error in temperature, and this shows the water vapor emission ratio in room square. And we can see that with different microphysics scheme, the Morrison scheme shows a smaller room square error in temperature at a higher level. However, below about 10 kilometer, it doesn't show a significant difference within all the 5 microphysics scheme, and also didn't show. We cannot see significant differences in the water vapor emission ratio. And we also do the similar comparison to using the RO refractivity. It also show a very similar pattern, something like this. So, and then we further compare these simulations to using the 18-hour forecast for the 3 typhoon cases to get a general verification to verify against the ERA5. So all the simulations, Wolf simulations, will be compared on the grid point against the ERA5. So we can see for the temperature, no matter using which initial conditions, with all the microphysics scheme, it's just show a very similar patterns in temperature. And however, for the water vapor emission ratio, it's also show very similar, but for the Goddard scheme, it's some kinds slightly reduce the root mean square error in the water vapor emission ratio, no matter using the ERA5 or Goddard scheme as the initial condition. So it's just give a double. It's just confirm that as the typhoon check is the Goddard scheme shows a better synapse scale simulations. Then next one, I will show some comparison result for individual case. So first one is for typhoon Brody. So we can see that this one is for the cloud top temperature. This one is the infrared image from the NHC enhancement image. So we can see the typhoon Brody is something pattern, cloud top temperature is something like this. This one is about negative 70 degrees Celsius. And all these 5 will show the simulated cloud top temperature from each, from different microphysics scheme. So we can see, for example, for the Purdue Lin and Thompson scheme, they all, both them shows the loose typhoon structure compared to the observations. And for the WSM6, it shows a solid vortex, but it's kind of a smaller coverage compared to the observations. Then for the typhoon, using the Morrison scheme, it shows a overly large circulation compared to the observation. So within these 5 schemes, we can see that the Goddard scheme seems to predict a better cloud top temperature compared with the observations. So this one is for the typhoon Brody. So next one is for the typhoon Metamor. We can see that the result just show a similar pattern, the similar conclusion with previous one, because the Morrison scheme is shown overly large, and the other is something like not well structured, and the Goddard scheme looks like more comparable with the observation. Then this one is for the third one for the composite. It's also just show the similar conclusion. So this all previous one just give a gross overview about the typhoon structure. So next one, we want to compare the Wolf simulation with the PRO observations. So since we already know that the simulated typhoon location have some errors compared to the best check. So before doing the comparison with the PRO data, we want to have some pre-processing. So here shows what we have done before the comparison. So first one, we will do the typhoon relocation. So we just move the simulated storm center and to be corresponding to the observations location. Then we also do the time interpolation that to be fixed as the PRO observation time. Then the third one is we want to considering about the cloud structure discrepancy, because the typhoon will spin, rotate. So we want to reduce that effect. So besides getting that, for example, this one is something like a red path from similar to the PRO data, according to the PRO data red path. We also, besides calculate the delta V along this red path, we also conduct the supplementary rays, offset this by about positive and negative 0.5 degree to get all these three delta V, and getting an average to obtain a representative result. So here shows the comparison result. Then this one is for the typhoon Brody. Then we can see that the bright line indicates the delta V from the PAZ PRO, and the different color indicate different hydrometeors, this is simulated hydrometeors. And we can get the total delta V to accumulate from the different hydrometeors, and something like would be indicate as the light blue line. So we can see the blue line is the total simulated delta V, then using that compare with the red line. So this one is a simulated delta V, and this one is observed delta V. So we can see that all from the Purdue Lin scheme, the simulated delta V is too small compared to the observation. And WSM6 is slightly improved, but still smaller than the observation. So the maxima from the past observation, the maxima delta V is about 35.1 millimeter. And here shows all the results from the maxima delta V from the other microphysics scheme. We can see that the Goddard scheme and the two more scheme, Thompson and Morrison, all show that comparable maxima delta V compared with the observations. And from this, we can also using this pattern to detect how the the simulated hydrometeors distributions in horizontal and vertical. And the gray line indicate the red path. So this one is along the red path to show the simulated hydrometeors for ice, snow, gravel, and others. In this study, we didn't count about the cloud water because cloud water is nearly spherical, and that cannot be detected by the PRO because of the measurement. Okay, so besides that, we also, from this figure, we still also can find that within all the hydrometeors, the snow contribute the most. For example, this red line is contribute the most compared to the other hydrometeors for the delta V. So since we find that for this typhoon Brody shows that Goddard scheme shows a most close to value compared to the observation. So for the next two cases, we just focus on using the ERA5 as the initial condition and using using Goddard microphysics scheme for the comparison. So we can see that for the typhoon metamorph, it also show a comparable pattern with the PRO data. However, for the compass case, we can see that it shows a significant deviation compared to the observations. So to further investigate why the simulated delta V shows a larger deviation, so we just do the verification against the ERA5, but separate for individual typhoon cases. So we can see that different line indicated for individual typhoon case, and this also show the 18-hour forecast. We can see this for the temperature room square error and the water vapor emission ratio room square error. For the yellow line indicated the room square error result from the compass, and we can see that no matter in temperature or water vapor emission ratio, the simulation from for the compass is always show larger room square error. So compared to the other two cases. So that indicated that in the synaptic scale for the typhoon composite, it cannot capture the larger scale well. Okay, so the next one, since the previous comparison will be only focus on the deterministic run, so to robust the result, we want to conduct a ensemble forecast. So we using to evaluate the hydrometeors in the typhoon is a challenge due to the high variation of the comparative systems. So here shows the 36 ensemble forecast. And this one just show the ensemble mean, ensemble variations and the ensemble mean. So this one is the color indicated the ensemble variations for the precipitation water. And the contour is the ensemble mean. So we can see the typhoon PRO is over here, and around this region it shows a larger variance from the ensemble members. So now here shows the result from the 36 ensemble runs. This one is the result from the ERA5 PRO with the Goddard scheme. So we can see that with the 36 ensemble forecast, it shows some differences in the cyclone circulation. This one is the simulated radar reflective simulation. So even, for example, the ensemble member 13th, it's just show not well predict for the cyclone circulations. But overall, we want to get a gross review about the result. So here just show the ensemble mean for the typhoon PRO. We can see that this is similar figure as previous show. And we can see that even the ensemble mean compare the blue line with the black line is also show a very consistent patterns with observations. And this green line, for each green line, it indicated the ensemble, each individual ensemble members. Then the blue line is the ensemble mean, and the light blue shaded indicated the one standard deviation. So we can see that with the ensemble mean, actually is more can cover most of the region, the pattern as the observations. Then this one is similar, but for the typhoon Medmore, and also it show a good patterns compared to the observations. Then this one is for the typhoon composite, because as we mentioned before, the typhoon composite in the deterministic run cannot capture well for the synaptic scale. Even for the now we conduct for the 36 ensemble members, it still cannot capture that well. Okay, so this one is the about the sensitivity test, because about the precipitation, we got some review comments asking about how about the planetary boundary layer scheme influence on this result. So we do the sensitivity test for the ERA5 Goddard and for the PRO case. This one is using the YSU PBS scheme. This one is the default as I showed previous one. Then the other four is a new test by using the same settings but change the PBL scheme. So we can see that all that result just show a very similar conclusion. And even there's some slightly differences, but the deviation with a different PBL scheme doesn't show a significant difference compared with the different microphysics scheme. So each indicator, the microphysics scheme make more effect on that delta phi. So finally, a conclusion. So from this study, the results show a significant variability in hydrometeors distribution influenced by the initial condition, microphysics scheme, and the typhoon location, circulation, and rainbands. So this study just showed the wolf simulation using the Goddard, Thompson, and the Morrison scheme that generally can pass the peak of the differential phase at the altitude close to those observed by the PAZ PRO. And we also conduct the ensemble experiment that ensemble mean also can capture most of the variability of the differential phase shift. So from this result, we can say that PRO observation has the potential to offer the variable guidance for the verifying hydrometeor simulations. Still, there's still some challenge in this study. So here we just mentioned some limitation of this study. So since we only have 3 PRO profile to compare with the 3 typhoon cases, we need, maybe in the future, we need getting more PRO data for other comparison to get a more robust result. And because we know that it's still a challenge to estimate the physical features precisely. For example, the turbulence, particle type, SS ratio, how to determine how for each individual hydrometeors, and also the orientation and so on. Then also there's still some uncertainties in vortex location and large-scale circulation and detail about the cloud microphysics and the model representativeness of the physical processing. So this result, what I showed today, we have submitted the result to the MT, and currently is under the second review. So hope we have some good news. So thank you.
Okay, we have time for questions. And I think the ceiling mics are on, so we don't need to throw our own microphone.
So a question for Hugh. So it seems that your scheme tend to have bigger angles. Why is that?
I could make a few guesses, but that was actually one question I had was, presumably this is related to cloud ice,
Yes. Yes.
primarily, and the differences between Goddard and Thompson,
Right,
and it sort of shows up with that hydrometeor phase thing you showed where
Yeah.
Thompson had almost no cloud ice,
Yeah.
and so, yeah, I would guess that it's some combination of, in the 2-moment schemes, we have to set an upper limit to the ice particle number, and the anvils are very sensitive to that. That's kind of like a, something like the 2-moment schemes just face, kind of like part of the sausage making process of microphysics schemes that, and then auto conversion, like in the Thompson scheme, auto conversion is very efficient from cloud ice and snow. So I think the results here are consistent with what I'd expect, I think, in these schemes and what other studies have shown.
Yeah.
So, yeah.
Yeah, I just wanted to say that in the Thompson version in 4.2, he put a factor for the auto-conversion of cloud droplet to rain, which reduced auto-conversion a lot in the 4.2 version.
But that was from cloud water to rain?
Yeah, I don't know if that has any impact on this, but it would be interesting to see the result with a newer version of the Thompson scheme, because he went back and because it reduced the auto conversion of rain a lot, but now it's a little bit more efficient.
Okay.
Thanks for the really interesting talk. So I think in usual radio occultation, when you get very low impact heights, it gets quite noisy with the like super refraction and things like that. Do you see a similar thing with the this polarimetric radio occultation?
Actually, we didn't use that traditional data for this one to compare because the comparison major focus on the delta phi.
So the observations aren't affected by the same things radio occultation or usual radio occultation are.
Yeah.
Maybe Sergey can respond to that.
Well, it's a challenge because this is using an accumulated phase and in the low troposphere, especially under such conditions in Chile, the signal is widely fluctuating and connected accumulated phase together is challenging actually. So that's, I would say, aside from superfraction and just strong fluctuation, we have had connected phase. The fact that there is reasonable agreement with observations shows that this is possible. This is true. I don't know what else to say. I'm not working on this technique.
Very nice presentation. I want to know if you have comments on future use of these observations into data simulation. Now that you probably have a forward model for this, if you have plan for warp DA or Jedi.
Yeah, good question. Actually, that's our next step. We want to have this operator to implement into the Wolf DA.
Maybe I'm misunderstanding, but as far as I understand, the PRO gives you essentially a phase difference between vertically and horizontally polarized waves. How do you back out all the microphysical species out of that? Because in those very nice parabola plots, I think you were showing model or where it shows like in red was snow, in blue was rain. Can you get this kind of plot from the observations too?
No.
No. So
we just
how could you use the observational data to inform the microphysics if they're doing the right thing?
Yeah, we cannot get the detail of the simulation of the hydrometeors, but we just can catch the total effect.
Okay.
Yeah.
But there may be some error compensation going on, right? Because it's not a one-to-one.
Yeah.
No.
line.
You're absolutely right. It's one equation with 7 unknowns. That's it. That's as simple as that.
Yeah.
And so, frankly, when we do a simulation of the radio occultation data, like refractivities or bending angles, those are also related to temperature, water vapor, and pressure and all that. And so when we assimilate those observations directly, the model, the data simulation system have to figure out the sensitivity, the relative sensitivity between the observation and different variables. And you also have to find the observational error, or the different variances. And so in the end, the data simulation system, yes, we will have only one value, that is the PRO differential phase. And then you have to project back whether that should be snow or ice or grapples. You would have to be figuring out the relative sensitivity of that parameter relative to different species, and also putting in the observational error. And then hopefully the magic will happen. They will just try to assign to the right.
It's like black magic.
Black magic, exactly.
I've got another question. Could you do the same thing with a ground-based receiver as well?
For
It should be, can you do the same as ground-based polarimetric radar?
for ground base, I
Well,
don't think so.
I think, let's check here. But I'm sure people have been using the polarimetric radars, right? And they've been trying to do a simulation of the polarimetric radar observations.
But could you receive the GNSS signals with a ground-based receiver? Does it have to be a low Earth orbit?
Ground-based receiver.
elevation, then those effects disappear because they're related to flattening, for example.
If you're,
Scenic, you won't have any effect. The effects will disappear.
if you're on a hilltop looking out on the horizon,
Oh, I see. The hilltop.
I do know that they are doing it from aircraft. So if you install an antenna that can get both on an aircraft, you can have.
Yeah, I think the hilltop, I don't think you can do it very well because you can only look down. So you cannot really see much. So you really need to have space-based system.
okay.
So I have a question kind of maybe similar to Falco's or related to that. For the simulator part, for getting differential phase, what is the biggest uncertainty? Like the aspect ratio in particular, are results pretty sensitive to that, I would imagine? Like if you vary that by, I don't know, pick some, I don't know what the uncertainty really would be, 10, 20, I have no idea, but how much would that change the results?
Actually, in this study, we already do our best to reduce the uncertainty because for the typhoon case, it's a lot of factors will impact this. And some paper also study that PL data compared with the AR system, atmosphere river, it shows a very good result because it's consistent precipitations. You don't need to consider about the circulation about the typhoon.
I think I was asking about the aspect ratio, I guess, of the particles. And how the assumption that you have going into that formula, like how, if that's varied, how sensitive are the results to that? Because that seems like one of the bigger uncertainties in this
It is.
method.
It is.
Yeah, so I think I said AR without
Yes.
making it clear. I
AR
meant
will be
aspect ratio.
sensitive. Yeah, I didn't prepare the figure because we also give the sensitivity test about the different AR value. It just show very significant differences. Yeah.
Because one thing with the two-moment schemes, because they, like in my scheme and in Thompson, two-moment for rain, in particular, they predict size, which could then maybe feed back into the aspect ratio parts. And so we know that, like for liquid drops, obviously aspect ratio is closely tied with the mean size.
Yeah.
Okay, are there any other questions? If not, let's thank Shu-Ya one more time.
Thank you.